Today we are walking through the paper titled Vector Policy Optimization Training for Diversity Improves Test Time Search.
What is the central problem this paper is trying to solve?
Modern language models are increasingly used inside test time search systems. Those systems sample many candidate answers and then choose the best one. The problem is that ordinary reinforcement learning post-training often teaches the model to give one narrow kind of answer, so extra search samples stop helping.
Why is a single strong answer not enough if the final reward is already known?
Because search works over a set, not one answer. If all candidates make the same compromise, the selector has little to choose from. If candidates cover different trade-offs, search can pick the one that best matches the deployment reward. The paper calls the proposed method Vector Policy Optimization, or VPO. Its goal is not just to raise one scalar training score. It trains the model to produce a small set of answers that spreads across a vector reward space.
On the left side, what is the difference between the black cluster and the blue set?
The black cluster is what scalar GA-RPO can do many samples, but they point toward almost the same compromise. The blue set is what VPO wants. Candidates scattered along the Pareto frontier, where one answer may favor objective 1 and another may favor objective 2.
How does the training procedure make the model produce a whole set?
Each rollout asks the model for multiple answers in one chain. In the experiments, the set's size is 3. Each answer receives a reward vector, such as separate scores for citation hops and answer quality, or separate scores for tool name and argument correctness.
The right side has many sampled weightings.
VPO samples many ways of weighting the reward vector. For each weighting, it asks which answer in the set is best. Then it averages those best in-set scores. A collapsed set only wins for a narrow range of weightings. A diverse set can win across many of them. The set reward can be written like this. It defines the score of an answer set S. Sample a reward weighting W. Score each candidate by the dot product between W and its reward vector. Keep the best candidate in the set, and average over weightings.
So the reward is given to the set, not separately to each answer.
Exactly. The paper then uses the usual group-based advantage machinery from GA-RPO, but the scalar score is this set level estimate. That is why the authors describe VPO as a drop-in replacement for the advantage estimator.
What do they compare it against?
The baselines isolate the ingredients. Scalar GA-RPO tests ordinary single-answer reinforcement learning. Multi-AR-LVR tests multiple answers with a fixed scalar reward. Random weighting GA-RPO tests changing reward weights without set optimization. MaxHK, MaxARL, and goal condition GA-RPO test stronger search-aware or multi-predict alternatives. The first result chart shows MuSQ and DUREQA. The axis is best 80K from K-sampled answers. Choose the answer with the highest scalarized reward. This is a simple version of test time search.
What pattern should I notice in these two plots?
In both domains, the VPO curve is the top curve at larger sample budgets. Scalar GA-RPO rises early and then flattens, while VPO keeps gaining from additional samples. The result supports the paper's main claim: diversity matters most when search has room to search. The appendix-style companion chart tells the same story on Metan to layer L. Maze is especially clear. VPO jumps above the scalar baselines by 3 samples and stays higher. To layer L starts near the ceiling, but VPO is still among the strongest methods as sampling grows.
Is the improvement really coming from diversity, rather than just better average answers?
The diversity plot answers that directly. It measures average pairwise distance between reward vectors in the candidate pool. VPO keeps or increases reward space spread during training, while the multi-answer scalar baseline is flatter or even loses spread on some tasks. The live code bench case study is a harder test. On the full held-out split, scalar GA-RPO has an advantage at 1 sample for pass at K. But as K grows, VPO catches up and overtakes. For best HK, VPO is above GA-RPO at every shown sample budget.
The right side uses an evolutionary search loop. What changes there?
On the hardest Petito coding problems, OpenEvolve with VPO solves for problems over 200 iterations. The same loop with GA-RPO solves IRO. That is the sharpest evidence that a diverse starting policy can unlock search paths that a collapsed policy never enters.
What are the main limitations I should keep in mind?
First, VPO needs vector-valued rewards, so it fits tasks where success naturally decomposes into components. Second, it is designed for settings where test time search is available. If you only ever use one answer, the benefit can be smaller. Third, some benchmarks start near ceiling performance, so the visible gains depend on task difficulty and search budget.
So the paper is not saying diversity is always free. It is saying diversity is valuable when search can use it.
Right. The paper's practical recommendation is to stop treating post-training as a race toward one preferred output. When deployment will search, training should preserve a diverse set of competent options that search can exploit.
That makes the result feel less like making one answer louder, and more like training the model to offer search a better menu.
Exactly. Vector policy optimization turns diversity from an accidental side effect into the training target. That wraps up this paper walkthrough.